In this video, I'll demonstrate how to take the second derivative of a set of parametric equations. That is the parametric form. I'll show the parametric form of the second derivative. And this problem is very similar to, it's the same set of parametric equations that I used for the first derivative of parametric equations. And that's so that we could build off of this. We have consider a particle whose position in meters is given by the parametric equations x equals 2t and y equals 4t squared minus 5, where t is in seconds. Now find the instantaneous acceleration of the particle at time t equals 4 seconds. Acceleration, not velocity. So the acceleration is the second derivative. So let's write that in this form. So that's the same. Now the second derivative of y, you could say it like that, or of the function, is the same as saying the first derivative of the first derivative. So taking the derivative of the derivative. Now, before I write what this leads into, I'm going to just remind ourselves what it means to take the derivative of something when you have the parametric equations. So I've got d dx of y, or dy dx. And when you have parametric equations, then you can break that apart and say that's dy dt over dx dt. So the derivative of the y function with respect to t and the derivative of the x function with respect to t. But we don't have the y function here. We have the first derivative of the y function. So what we can do is, let's just to show what I'm doing here. This is this y. I'm putting this dy dx in the place of this y. And then I'm going to write everything else kind of the same. So it's going to go right here. Okay, so that is equal to, I'll say, d dt, with the derivative with respect to t of dy dx over dx dt. And again, I'll highlight this to show where that all follows. Okay, I've just substituted the dy dx in for the y. Okay, so it still follows that same rule. It's like we're doing the first derivative all over again, but we're just doing it again. So building from that last video, we found that dy dx, I'll just write that down, dy dx, because we're going to need that, equaled 4t. We found that to be the case. So I'll just put a box around that. That's not the final answer, but we're going to need that for right here. So now what I'm going to do is take the derivative of that with respect to t. So the derivative with respect to t of 4t, well, that's an easy one. That's just 4. And then we also have to find dx dt. So the derivative of the x function with respect to t, and just to show what that is, that's x equals 2t. So the derivative with respect to t of the 2t, that just equals 2. Those were some easy derivatives. And now we've got the 4 and the 2, so we're going to plug this back into here. This equals, let's color code this a little bit. This numerator equaled 4, and this denominator equals 2. So we've got 4 over 2, and so the second derivative, then that is the instantaneous acceleration, rate of acceleration. The second derivative equals 4 over 2, or just 2. Right? I've just simplified this. So 2. Let's put a label on that, 2 meters per second squared. And then you're saying, hey, what about this time t equals 4 seconds? Well, if we had a t in this second derivative, absolutely, we would plug 4 in wherever we see t, but we don't have a t there, so we are done. The acceleration, the rate of acceleration, is actually constant for this particular particle.